Hello everybody, this is Rudra Pradhan here. Welcome to Engineering Econometrics, and today we will continue with Descriptive Econometrics, and that too we start with the same discussion that is on covariance and correlations. In the last lecture we specifically highlighted the covariance issue and the correlation issue to know the kind of requirement, the kind of need as per the engineering econometrics is concerned, and we have gone through the particular process to know how to calculate correlation coefficient, how to interpret, and what is the beauty of this particular kind of component. So ultimately whatever we have discussed in the last lectures, that is related to simple correlation structure, and that too between two variables only, that is exclusively bivariate game. But in reality most of the engineering problems can be connected with more number of variables. So as a result correlation can be applied in a multiple situation, means multivariate case, where we may have the situations of 3 variables, 4 variables and so on. So that means typically more than 2 variables. If it is only 1 variable case, then we cannot use this technique, but if it is 2 variable case, we can absolutely use this technique, provided there is a need of that technique and the kind of requirement. If there are more number of variables, then we can still use this particular technique, and then we connect differently. That is how the issue of covariance matrix and correlation matrix is coming into the picture. So when we talk about covariance matrix and correlation matrix, so then any variables you have, by default you can obtain this particular matrix. For instance, if it is 2 variables, so you will have a matrix of 2 into 2. If it is 5 variables, then you will have a matrix of 5 into 5, where you will get 5 cross correlations, where we will have a kind of covariance matrix and variance matrix, where the 5 variance issues and different covariance issues. Typically if it is 5, then the cross correlation coefficients will be 5C2. So these are the things we have to know, and you have to calculate accordingly. But in the meantime I will let you know how is the particular structure. So this is what we have discussed in the previous lectures. So ultimately data analysis and correlation. So what we have done, actually we just indicate the variables and the data range. Ultimately software will help you to report the correlation coefficient, and that too in the case of bivariate structure. And in the same times, if you have multivariate structure, again you just highlight the entire variables with the particular range. By default the software will give you a correlation matrix. So what we have already mentioned, if it is a 2 variable case, you will get a matrix of 2 into 2. If it is 3 variable case, you will get 3 into 3. So that means every time it will give you a square matrix format. And the beauty of this particular format is like this. Let us start with the examples here. 2 variables 1 2 and 1 2. So here we have a correlation matrix of 2 into 2. So this is actually correlation upon same variables, and as a result this will be always actually 1. So when you correlate same variables, then the correlation coefficient will be 1. So as a result all the diagonal elements of the correlation matrix will be always 1, and the off diagonals are always actually give you the correlation coefficients, and the off diagonals are the major requirements or the kind of basic inputs to the regression modeling or the further engineering econometrics processing. So here if the issue is prepare either a covariance matrix or a correlation matrix. So the difference is like that, in the case of covariance matrix all the diagonal elements are not standardized, but in the case of correlation the diagonal elements are standardized. Whatever may be your sample size, or whatever may be a kind of variable size, so your diagonal elements will be always represent 1, and off diagonal elements or on diagonal elements will be in between -1 to 1 only. So, it may be 0, it may be say 0.43 or 0.47 or something like that. It may be positively linked or it may be negatively linked, but ultimately the values will be coming in between -1 to 1 only, but all the diagonal elements will be always 1. So, that is the beauty of correlation matrix in comparison with the covariance matrix. So, that means technically when you solve any kind of engineering engineering problem by using engineering econometrics. So, first you report the univariate statistic, bivariate statistic, then you look for the complex modeling to investigate the problem more accurately, and that too in a kind of in depth kind of way. So, so the particular matrix will give you beautiful signal through which the model will be more active, or you can think about the more strength about this particular models. Otherwise, without any such evidence, so you are connecting any models or using any model for the investigations, sometimes there may be error in the later stage. So, having basic background, so it will give you better results, better inference to the complex analysis. So, ultimately, so this is how the particular processing. So, then what is the what see here. So, what is more about this particular structure is, so this is actually 6 variables case, and what I have already mentioned in the you will get a correlation matrix of 6 into 6. So, see here, so all these diagonal elements are 1 1 1 1 1, and off diagonal elements are in between -1 to 1. So, this is negative, this is positive, this is negative, this is negative, this is positive, this is positive. So, ultimately, so what I mentioned, so you will find 6C2 correlation coefficients you can obtain from this particular matrix. And the beauty of this particular matrix is that you have to just report the on diagonals, and the transpose of on diagonals will be the off diagonals entry. So, that means if you have two correlation coefficient x1 and x2, so we can either call as R12 or we can call R21. So, both will be having same results. So, that is how correlation coefficients are technically called as symmetric in nature. So, similarly, if you connect with standard deviation sigma 1 2 and sigma 2 1s, they are also same. So, ultimately, so the diagonal elements can be actually transposed, and then you can get the full correlation matrix. Ultimately, if all these reporting are there and these are not available, so it is not an issue, because this same value will be appearing here. It is actually double double kind of an entry, and there is no need to actually go for double entry. That itself will indicate the particular relationship. That means technically we are starting from left to right, and other side you will start with right to left only, but ultimately we need that particular point. What is the association? That means technically what is the association between 1 with the 2 and 1 with the 3 or 1 with the 4. Similarly, 2 with the 3, 2 with the 4, and similarly 3 with the 4. So, that means technically, so if there are 6 variables, say 1 2 3 4 5 and 6. So, that means the relationship will be like this: 1 2 1 3 1 4 1 5 1 6. So, that means technically the correlation coefficient will be 1 2 3 4 5. So, in the first instance you have 5, and again you connect with the 2 3 2 4 2 5 2 6. So, it will give you 4 more. So, again you have a 4 more. So, then again you start with 3 4 3 5 and 3 6. So, it will give you 3 more, again 4 5 4 6, 2 more, and then finally 5 6 1 more. So, these are the total correlations you will have. So, it will be 9 12 and then 3 15 correlation coefficients you will find here. So, you can, if you count all these things, then by default you have a 15 correlation coefficients. So, ultimately it will give you better understanding about these variables involved in the particular econometric modeling process. So, then ultimately we will move, and what is more about this particular process is like this. Sometimes what happens means what I have already pointed out. So we are living in a kind of scenario or dynamic worlds where more number of variables can come closures or can associate each other. So you may start with the two variables, but ultimately there are other variables may be treated as push factors or pull factors which can affect this relationship. That means at the end of the day we will find multivariate structures. So if it is a multivariate structure, still correlation can be used. So 1 to 1, so like whatever we have a correlation matrix we have already discussed, that's the actually a matrix of 6 variables, but ultimately the reporting is 1 to 1 only. So that means variable 1 with variable 2, variable 1 with variable 3, variable 1 with variable 4, variable 1 with variable 5, variable 1 with variable 6, and so on. So ultimately, so we are targeting each variables different different levels, but there may be actually a kind of issues or something like structure where all the variable simultaneously can be linked. So that is how the correlation structure can be of 3 types. One is called as simple correlations, where we have 2 variables at a time. It may be 1 2 or 1 3 or 1 4 or 2 3 2 4, something like that, or maybe all variables simultaneously. So as a result, simple correlations and something called as a kind of partial correlation or multiple correlations. So one of the classic example here is the partial correlation coefficient. So partial correlation coefficient structure is we are connecting two variables with the third variables as a kind of interactive kind of structure. So that means with the presence, let us say I can write like this, R 1 2 3 means, so I can prepare a structure like this. I can prepare a structure like this, for instance. So R 1 2.3, R 1 2.3, then I can put R 1 3.2, then R 2 3.1. So like this there are 3 partial correlation coefficient we can have. So ultimately, so the partial correlation structure will be like this. So this is how the kind of structure is, means for a 3 variables scenario the structure will be like this. If you have more variables, then you just add up like this. So this is how the path diagram for partial correlation or multiple correlation. But ultimately the issue is you are just reporting the correlation coefficient between two variables in presence of other variable, what we call as interactive effect. Sometimes it's in real life there are instances where we need actually reporting partial correlation coefficient rather than simple correlation, because if you apply simple correlation in that scenario, then your output will be very biased and it will not give you correct inference and correct kind of output to address the particular engineering problems as per the need or requirement. So for instance, you are just establishing the relationship between a price and quantity. So there are lots of theory. If you increase the price, then quantity will be down. If you decrease the price, then sales quantity means the sales will be high. So that means a theorem says that management in the management field or kind of engineering economics field. So the sales and price, what we call as demand theorem, where price and quantity are inversely related to each other. So that means this will give you negative correlation coefficient. So the simple interpretation is that if you increase the price, then sales will be down. If you decrease the price, and sales will be up. It's not always true, but many instances the theorem holds true. So now what is happening? This relationship, the inverse relationship, can be very active, provided if there is a third variable in the pipelines. For instance, you are increasing the price level and decreasing the price levels, and you are doing at your organization, and you are not informing anybody else. So that message should go to the actually customers or the kind of consumers. So whatever changes you are applying, so this message should go to the consumers immediately, so that the theorem can means whatever strategy you are applying, that will work in the market. If you are not, if whatever your strategy you are applying, and if that message will not go to the consumers or customers, so ultimately your strategy will not be very active. So that is how it is your duty, whatever strategy you are applying for the customers and consumers, so you have to communicate properly. So that is how the issue of advertising will be coming into the picture. So that means whatever message you like, means whatever strategy you like to apply, so you create awareness among the people. So that's why I put either in the form of advertising or something like that. So as a result, this message will immediately go to the consumers. So technically, in such a kind of scenario, so advertising expenditure is the kind of control variables. So when I am writing R1 2.3, so 3 will be the control variable. So with the simple interpretation is that with the assumption that, or with the condition that we are putting the advertising, that there is a price change, whether it's downward or upward, and how is the relation with sales. So that means advertising is the control variable here, and having advertising is the control variable, what is the price and quantity relationship. If you remove this advertising, then there will be relationship, but the relationship will not be perfect. But because here the issue is the interactive effect will be coming into the picture, because without any such control you cannot actually establish this relationship, or you can establish this relationship, but this relationship may not be very perfect. For instance, means another way I can highlight, for instance, suppose you like to put more hours in a particular work, then obviously productivity will be very high. Now I start with let us say daytimes 8 o'clock, and working hard, and obviously production will be increasing, productivity will be increasing, but working hard and productivity may be actually positively related to each other. So if you spend more time in production, then obviously production will be high, but ultimately you cannot do the continuous productions or continuous involvement until unless the infrastructural availability is there in the system. So that means one of the typical requirement to sit longer hours or to involve longer hours in the production process to have more production is the infrastructure. For instance, the let us say power, electricity. If electricity is there and the facilities, let us say AC facility is there, then you can in a position to sit long times or involve long hours and look for more production. So here the infrastructure is the control variables. Having the infrastructure, so you may be in a position to sit long times, involve long times, and look for more productions. So that is how means these are the areas where so the multiple correlation or partial correlation come into the picture. Sometimes all the variables jointly can influence each other. That is how multiple correlation coefficient come into the picture. For instance, I will take 3 variable case for better understanding. So this is how the case, and this is how the case. So this is how the perfect path diagram for partial and multiple correlation, and this common zone is nothing but called as multiple correlation. And when we look for actually partial correlation, let us say this is 1, this is 2, and this is 3, and ultimately so this area is called as a R1 2.3. so that means technically this common interaction should be actually controlled. So then with these controls, what is the relationship between the two? So when I am talking about R1 2.3, so that means I am talking about this point only. Similarly, when I am targeting about actually the correlation between 2 and 3, so this is the area where R 2.3 and the control variable is the 1. So these are all actually called as partial correlations, and the common zone is called as multiple correlation. So that means multiple correlation coefficient represents or the kind of interpretation is that it gives the simultaneous kind of combined association between these three variables. That means they are connecting each other. Actually, absence of a particular variables may affect the relationship significantly or considerably, you can say. What is happening here? So means the issue is very simple. You have a simple correlation, you have a partial correlation, you have multiple correlation. In fact, multiple correlation structure will be discussed in details in regression modeling. Similarly, partial correlation is also there in the regression modeling. In the regression modeling, we call as regression coefficients, so where we have some kind of control mechanism. Partial regression coefficient we have to calculate and report. But here, before we go for regression modeling, still we can report these things, and you can find out the particular requirement, understand the problem more accurately, and visualize as per your requirement. That is how I have actually elaborated the kind of items, that is the partial correlation and multiple correlation, in addition to whatever we have discussed the simple correlation. And I have also cited a couple of examples where you can apply partial correlation, where you can apply multiple correlation, and sometimes there you have to apply the particular tools as per the particular requirement and the need. You cannot just blindly use the technique and apply some somewhere and then get the kind of results. And this is the process which is completely biased actually, and the particular inference and the particular output will not be very active and efficient. So that is how you should know the details, understand the particular technique, understand the problem area where you can apply, and then look for the particular outcomes as per the requirement and the need of the engineering problems. So ultimately, so this is how the called as partial correlation coefficient, and likewise this is a kind of multiple correlation coefficient. Here the signal is actually like this, let me once again highlight here. So three variables. So partial correlation will be R1 2.3, R 1 3.2, then R 2 3.1, and similarly these are all partial correlation coefficients with respect to three variables, variable 1 1, variable 2 2, and variable 3 3. So then in the case of multiple correlations, you will find R 1.23, that means this is a control variable. So this is actually solid a component for regression modeling, because in the regression modeling we start with actually bivariate, because like correlation and covariance, the minimum requirement of regression modeling is two variables, where one will be dependent variable, another is a independent variable. For instance, when I am writing R1 2, so assuming that one is the dependent variable, 2 is the independent variable. For instance, I will write like y equal to f of x. So that means this is the independent variable, let us say 2, and this is 1. So now correlation coefficient will also give this similar kind of signal. So when I am writing multiple correlation coefficient, that to R 1.23, so that means R is the kind of base, then it will be connected with variable 2 and variable 3. Similarly, I can change the domains. I can put R 2.13 and R 3.12 like this. So these are all called as multiple structure through which you can actually look for the particular investigation and the kind of econometrics output to address these problems as per the particular need. So this is how the actually which I have already in fact highlighted, and this is how the particular structure through which you can understand the partial correlations and multiple correlations. Ultimately, whatever we are discussing, whether simple correlation, partial correlation, and multiple correlations, so every time the range will be unique or uniform. For instance, the range will be -1 to 1 only. So if there is association, so you will find they are not equal to 0, and the values will be in between -1 to 1, that to like 0.095 or 0.005 or -0.025, something like that. and if it is close to 1, highly positively correlated. If it is close to -1, highly negatively correlated. If it is close to 0, then it is low associations. If it is let us say close to 0.5 negative or positives, that means it is a medium range association. So, that is how the interpretation will be different, and then you understand the problem as per your requirement. So, that means technically whatever we have discussed till now, it is the kind of bivariate structure between covariance, correlation, and with the intention of simple correlations, then partial correlations and multiple correlation. And in addition to these econometric output, these are all called as econometrics output. Correlation coefficient is a kind of econometric output, whether it is a simple one or whether it is a partial one or it is a kind of multiple one. And what is happening here, once you get the correlation coefficient, to validate the particular structures, what we like to have, you have to statistically test it, and there is a need of statistical signal. So, whatever we are getting, it is just statistical output. Until unless you validate and test, you cannot just declare, or you cannot just go for applying it. So, that is how the structure called as inferential econometrics, and that too otherwise called as hypothesis testing. The hypothesis testing is very straightforward, which I have slightly highlighted in the last lecture. Set the null hypothesis with the assumption that the correlation coefficient not equal to 0, but ultimately the data is saying that there is a correlation coefficient, and then you specify the probability level of significance to test the particular test statistics. So, as per the econometrics requirement, most of the instances we use 3 levels, 1%, 5% and 10%. So, what is happening in the testing procedures, if you go by manual procedure. So, we have actually statistical tables, that is called as a benchmark values with the different probability levels, and that depends upon corresponding degree of freedom. Ultimately, in the next lectures I will highlight in details. So, ultimately hypothesis testings, there are three four things are very common. So, you have to choose the probability level of significance, that is at the 1%, 5% and 10%. Then we have to choose a particular test statistics. For instance, we are getting R square here. R square is not a test statistics. We have a different test statistic. For instance, we start with Z statistic, T statistics, chi square and F. Ultimately, so in the inferential analytics or inferential econometrics, the test statistics follows. Let us say we have a chi squares and then Z, T and F. So, these are all very standard for test statistics, and most of the instances correlation and regression we frequently use actually T statistics. So, that means when you get a correlation coefficient R with respect to two variables, say R12, that is 0.35. So, that does not mean this is a statistically supportive. So, we need to test it actually. So, there is a test formula. So, for that there is a you need to calculate T statistics, and it depends upon in fact like correlation coefficient R, we have a formula. So, you have to calculate a TR12. So, then there is also formula how to calculate. For instance, the formula of correlation coefficient testing is like this. So, this formula can be used to test whether correlation coefficient will be statistically significant or not. So, this will give you test statistics value on the basis of whatever correlation coefficient you have reported, and that too depends upon the sample size and degree of freedom. And so, once you get this is what called as a calculated test statistics, and then you can compare with the tabulated statistics. We have a T tables, and in the T tables it is a benchmark values, and the tables will be with respect to probability level of significance. We will find 1% level, 5% level, 10% level, and sometimes in between, and then that depends upon the sample size, what we call as degree of freedom. Generally, degree of freedom is the difference between sample size and the variables involvement, usually called as n minus k indications. N represents sample size, K represents number of variables involved in the investigation process. So ultimately degree of freedom is the balance between means balance it between N and K. So that is the sample size and the variables involved. So when your sample size is high and variables involvement will be low, then your degree freedom will be very high. Ultimately we need actually high degree of freedom to to justify our validation. So that means every time when we are going for testing, our main intention is to reject the a null hypothesis, which we start with that there is a no value, but ultimately there is a value, whatever value we have, that need to be statistically significant. So that means one way to justify is that you must have high degree of freedom and you must have also high correlation, then ultimately you can actually reject. So the comparison will be calculated test statistic and tabulated test statistic. So the tabulated statistic depends upon probability level of significance. So like this, so the tabulated value will be, this is a degree of freedom, then probability level say 1%, 5% and 10%. So there may be in between, but I am just reporting the major ones. So you start with the degree of freedom 1, 2, 3 and so on like this. So then you will find reported figures. So that means technically the tabulated statistic corresponding to this calculated depends upon the degree of freedom and the probability which you have fixed. So that means ultimately you just get to know what is the degree of freedom, then you try to report test at tabulated value of this particular test statistics at 1%, 5% and 10%, and that will be at a particular degree of freedom. So because a degree of freedom will be remain constant for 1%, 5% and 10%. Let us say it is actually degree of freedom is 20. So you just check what is the value of 1%, what is the value of 5% and what is the value of 10%. So ultimately the rule is that the benchmark value will be very high at 1% and it will be slightly lower at 5% and again slightly lower at 10%. So that means technically our job is to check whether your calculated test statistic will overtake the tabulated statistic or not. If it is the case, then you are in a position to reject the null hypothesis and justify that this particular item is statistically significant. So once you get that particular signal or evidence, then you can apply and give a kind of policy implication or judgment, something like that. But having only statistical output will not actually solve your engineering problem. And so this ultimate solution depends upon the econometric output, and this econometric output need to be tested empirically. That's what is called as hypothesis testing, or it's called as inferential econometrics. So the standard rule is use a test statistic corresponding to this econometric output like covariance and correlation, and then with the help of a sample size, number of variables and the probability level of significance, you have to find out the tabulated value and then compare the calculated with the tabulated with different probability level, then check at what positions you are in a position to reject your null hypothesis, and ultimately you can conclude the kind of requirement. So if you do like that, then you are in a right track to address the problem as per the particular requirement. And this is what the standard procedure, and you have to apply this one with the case of simple correlation structures, partial correlation structure and multiple correlation structure. Again, the same testing mechanism is also equally applicable in the context of say regression modeling. So in the regression modeling, so the typical link is a little bit different, because where the objective is to work out the causality kind of issue. So that means the issue is the cause and effect, but here we just establishing the relationship, whether association, no association, relationship, no relationship, but ultimately we are not bothered about which factor is cause and which factor is effect, but which is very much essential in the real life scenario. Without knowing which one is cause and which one is effect, so the future plan or future kind of implications you may not actually apply accordingly. So your planning and the strategy depends upon all kinds of output or the kind of clues. So there is the relationship, the kind of cause and effect kind of links. So again the cause, who is more, who is less, and who is negative, who is positive. So you need to balance actually all these things ultimately to optimize your engineering objectives and the kind of problem requirements. Once you do all these things, then you are in a right track or right balance to address the problems as per your particular requirement. So ultimately till now whatever we have discussed, it is all about the univariate structure or univariate statistic and bivariate statistic, and both are very essential for advanced engineering econometrics problem. So in the advanced engineering econometric problems, we frequently use regression modeling with a different kind of functional from different kind of structure to analyze the business problems or engineering problems as per the requirement, objectives and the organizational goals. But ultimately to strengthen our process or the kind of movement, so the basic statistics or univariate statistic and bivariate statistic or bivariate econometrics will be very handy. So ultimately till now whatever we have discussed, it is all about understanding the engineering problem, how you can quantify the engineering problem, how you have to address the problem or develop a models through which you can analyze the issue more effectively. So typically we need to identify the variables through which you can quantify the problem, then to establish the link or the kind of measurements. So we need actually data corresponding to each variables. Then with the help of some basic econometrics and bivariate econometrics, we need to have a what we call as intermediate output. So these are all called as intermediate output. It's not final output, econometric output, because final econometric output will be something different, because our this subject objective is engineering econometrics, where the causality issue is more important rather in comparison with simple descriptives, means univariate reporting and the bivariate reporting. So ultimately our main aim is causality issues among the variables in a particular setup, in a particular engineering problem. Ultimately whatever we are knowing all these basic statistics, basic econometrics or bivariate statistics, bivariate econometrics, various softwares, spreadsheets and the data structures, all these are actually requirements. These are all we can call as basic infrastructure for the engineering econometrics. So until unless you clear about all these basic infrastructure, if you are not acquainted with all these infrastructure, so then you may not actually play in the game in the engineering econometrics. In order to become a big players in this domains, so you must have this kind of understanding, and your hand must be very active in all these aspects. It's not a big deal actually having the problems if you once quantify properly with respect to variables, having the data. So these are all kind of 1 or 2 minutes job only with the use of softwares. So just allow the software to report, then a software within 1 minute will give you the econometric output. Ultimately it is you to understand and connect as per your requirement. But until unless you know all these things, software will not help you. Software will just need your command to help you to get some kind of output, and it is you to actually how you have to interpret and how you have to use this intermediate output for final output processing. And that is how we are actually discussing these issues or the kind of tools and techniques. In the next lectures we will give we will discuss something more about the inferential econometrics, where we need to understand the use of probability distribution, sampling and sampling distribution, because ultimately the issue of engineering econometrics is nothing but sample specific. It is not actually ultimately population specific. In 99% instances we use actually sample, and then we analyze the samples and then finally on the basis of different sampling outputs with different robustness checks, we have to generalize as per the particular requirement. And for that, all these basics are essential. So that means in the next lectures we should understand, or we should get to know, or we will be acquainted with the all kinds of inferential econometrics, so that the predictive econometrics can be more handy while you are solving any kind of engineering problems. So with this we will stop here. Thank you very much. Have a nice day.